This video demonstrates that the theory of the relativity of time and the theory of the relativity of motion contradict each other, actually negate each other. Einstein tells us that the rhythm of a clock is affected by its velocity. The faster the clock moves, or the body upon which it is fixed moves, the slower the rhythm of the clock. In The Evolution of Physics, he states the following, and I quote, "The changes become more distinct as the speed increases. The rhythm of a moving clock is slowed down compared to the clocks it passes along the rod, and would come to stop if the clock were to move with the speed of light." However, Einstein's theory of the relativity of motion is incompatible with the theory of the relativity of time. In his book, Relativity, he states the following: "The basal principle, which was the pivot of all our previous considerations, was the special principle of relativity. That is, the principle of the physical relativity of all uniform motions. Let us once more analyze its meaning carefully. It was at all times clear that from the point of view of the idea it conveys to us, every motion must be considered only as a relative motion. Returning to the illustration we have frequently used of the embankment and the railway carriage, we can express the fact of the motion here taking place in the following two forms, both of which are equally justifiable. A, the carriage is in motion relative to the embankment, or B, the embankment is in motion relative to the carriage. In A, the embankment; in B, the carriage serves as the body of reference in our statement of the motion taking place. If it is simply a question of detecting or of describing the motion involved, it is in principle immaterial to what reference body we refer the motion. Although the body of reference relative to which the motion occurs, in A the embankment and B the carriage, is not necessarily at rest relative to other bodies in the universe, if it is to serve as the body of reference and therefore the basis of the measure for the motion of the other body, it must be effectively at rest regarding that particular motion. Therefore, stated briefly in the simplest case, if A's position changes relative to B, we can state this as two different but equally justifiable motions. A is a motion and B is at rest, or B is a motion and A is at rest. Indeed, according to Einstein, there is no way of determining which body actually moves. In relativity theory, there is therefore no such thing as actual motion or motion of an independent trajectory. But if it does not matter when two bodies, A and B, change their positions relative to each other, whether we say that A is in motion and B is at rest, or as justifiably that B is in motion and A is at rest, how is the clock supposed to know whether it is the one in motion or the one at rest? If we fix clocks on A and clocks on B, which are in motion relative to each other, and assume that A is in motion and B is at rest, then it would have to follow that the clock on A is moving with a slower rhythm than the clock on B. If, on the contrary, we assume, as we are permitted to according to the basal principle of relativity, that B is in motion and A is at rest, then the clock fixed to B would be moving with a slower rhythm than that fixed on A. Unfortunately, even the theory of relativity cannot make clocks perform such maneuvers, and clocks are the only way we have of measuring the advance of time. Indeed, are all those tales of people aging slower than the people on Earth while speeding along in rocket ships merely science fiction? Because by simply saying that the rockets are at rest and the Earth is speeding along, the aging process would be transferred from one body to the other. And if we had a friend with us whose sense of convenience differed from our own, could he be making the people on Earth age slower while we were making them age faster at the same time? The clock's rhythm cannot depend on which body we are assuming at the moment is in motion and which at rest. The theory of the relativity of time must be based on a theory of motion that does not conform to the principle of relativity, because the relativity of time assumes the necessity of knowing in a definite and uninterchangeable way which body is in motion and which at rest. In other words, it depends on the theory of an independent trajectory of motion. Otherwise, it would be impossible to determine which clock has the slower and which the faster rhythm. Indeed, if the theory of relative times was valid, and in my opinion it is not, By comparing the times, we could establish actually and uninterchangeably which body was in motion and which at rest. The body that had the slower clock would be the one that was in motion. This would, of course, result in the immediate demise of the basal principle of relativity, that is, the theory of the relativity of motion. But there are further difficulties with the theory of the relativity of time. If any body is moving relative to another body, and it must in order to be in motion according to the principle of relativity, its time will always be faster or slower than that of the other body. Therefore, it will never be contained within the same time as the other. But then the question arises whether they can be in motion at all. For if a body can only be in motion relative to some other body, we're always assuming that this relative motion is occurring in the same time. For to say that A is in motion relative to B, but that A does not exist at the same time as B negates the possibility of the motion. The difference in the rates of time, according to relativity, occur because of and during the motion of one body relative to another. When the relative motion comes to an end, the different rates of time also come to an end. However, if, according to Einstein, and I quote, by the motion of a body, we always mean its change of position relative to a second body, unquote, then there is always a common time between the body that is moving and the body relative to which it is moving, and this is the time of the relative motion. This common time must exist throughout the motion, that is, from the beginning to the end, and throughout all the intermediate points. For wherever the common time doesn't exist, there can be no relative motion. Therefore, whatever numbers the relativists are assigning to the different bodies, the latter share the common time which is determined by the existence of the relative motion of which each body is a necessary part. Thus, the theory of the relativity of time must assert a common time for both bodies, which is the time of the relative motion, that in turn determines supposedly the different rates of time that supposedly negate the common time that determines them. It's a mess. Well, you can't have your cake and eat it too. Uh, I thank you very much for uh, for listening to this. I know a lot of it gets a little dense, but I appreciate your time. And as Gene Autry used to sing, happy days to you until we meet again. Thank you again.